In this video, we analyze the spectrum of a conventional amplitude modulation when the modulating signal, the information that we want to transmit, is a deterministic signal. The analytical expression in the time domain of a conventional amplitude modulation is the addition of the carrier and the product between the modulating signal with modulation index A, MA of t, and the carrier. This modulating signal with modulation index A, MA, is just a normalized version of the modulating signal. The normalization factor is the ratio between the modulation index A and the range of the modulating signal. Thus, we can avoid the overmodulation effect. With this expression, it's relatively simple to obtain the Fourier transform, the frequency representation of the conventional amplitude modulation. We only need to take into account that now the Fourier transform of the signal MA is related with the Fourier transform of the modulating signal, taking into account the scaling factor A divided by Cm. Now, the spectrum, the Fourier transform, is the Fourier transform of the cosine and the Fourier transform of this term plus the Fourier transform of this product. If we have a product in the time domain, we have a convolution divided by 2 times pi in the frequency domain, the convolution of the Fourier transform of MA and the Fourier transform of the cosine of the carrier. The Fourier transform of a carrier is just given by 2 deltas shifted to omega c and to minus omega c with the corresponding phase factors introduced by the phase phi c and with amplitude, the carrier amplitude times pi. Then the convolution of these deltas with the Fourier transform of MA produce just shifted versions of the frequency response of NA, shifted plus and minus omega c with the corresponding phase factor, and each replica has an amplitude scaling of 1/2. If we analyze now this expression, what we have is that the Fourier transform of a conventional AM modulated signal is given by a pair of deltas at plus and minus omega c and 2 shifted replicas of the spectrum of MA, shifted plus and minus omega c. This is summarized here. The 2 deltas and the 2 shifted replicas of the spectrum of MA, which is proportional to the spectrum of M. And the phase of the carrier is introducing some phase shift terms, complex exponential of plus and minus j phi c. They are linear phase terms. One of the most important conclusions that we can obtain from this analysis is related with bandwidth. The bandwidth for a conventional amplitude modulation is twice the bandwidth of the modulating signal, 2 times W radians per second, or equivalently 2 times V hertz, twice the bandwidth of the modulating signal. It is very easy to see this with a graphical example. For instance, if here the Fourier transform of the modulating signal has this frequency response, a rectangle between minus the bandwidth and plus the bandwidth of the signal, then the Fourier transform of the modulated signal is this one. We have the deltas corresponding to the Fourier transform of the carrier, these 2 terms here, and then we have 2 shifted replicas of the spectrum of M scaled, the corresponding scaling factors, and located at plus omega c and minus omega c. In this case, it's very simple to see that now the bandwidth of the modulated signal is twice the bandwidth that we had for the information that we transmit. And this happens independently of the shape for the Fourier transform of the modulating signal. In this case, we have another example with a triangle response, but the bandwidth in any case is twice the bandwidth of the modulating signal. This is one of the main characteristics of a conventional amplitude modulation.